In this video, we're going to work example problems where we perform fundamental math operations with complex numbers. So adding, subtracting, multiplying, and dividing complex numbers. Okay. Now, when going through the textbook, we talked about how you're supposed to view the imaginary number I. And the way that I suggested you should think about it is that you kind of imagine that I is like a variable. But someone made a comment that I should perhaps be careful with mixing the term variable with I. And I get what they're saying. I tried to make it explicit that I is absolutely not a variable at all. Okay, but what I meant was that, and the commenter suggested, let's see, the commenter was Soch023. He suggested it would be a better idea to compare I to, like, if you had pi in an equation, or e, right? These are just pure numbers, right? But how do you operate with pi and e in equations? Like if you had pi times 5 minus 2x. Well, you could leave it like this, but if you wanted to distribute it, you do this. And all I meant by saying that it was like a variable, I just meant in terms of the way you kind of operate with it, in that you can't, like here, you can't simplify this anymore. But if you had you can combine like terms. It's kind of like 3 pi and 4 pi are like terms, and you can get, that's all I meant. Okay, but really the main point of this is that it's really, you're going to treat I like it's any other number. You don't have to be scared about, well, what are some rules? The rules must be different when it comes to an imaginary number than an actual real number like pi or e. Not at all. Not at all. I obeys the same like exponent properties. So I squared times I to the 6th would be I to the 8th. Everything's the same. The only big nuance that we've talked about when it comes to complex numbers mixed in with into equations, etc., with real numbers, the big nuance is that you don't want to leave a term like minus root 16. You don't want to start applying properties to this and doing math with this, multiplying or dividing an equation by the same thing on both sides, etc., with this as it sits. Whenever you haven't accounted for the imaginary component that's mixed in here, you want to find all terms that have something imaginary like mixed into it and go ahead and take out what's imaginary about it. Then proceed forward. That's the only big nuance when it comes to working with imaginary numbers mixed in with real numbers in an equation or whatever, any kind of math system. That's the only nuance. You don't want to start applying math properties and math rules and adding things to both sides of the equation, multiplying things, doing all kinds of stuff like that. You don't want to be doing any of that with terms that you haven't accounted for, if there is an I mixed in that you need to account for without having accounted for that yet. You don't want to do that. Because it's like if you have minus 4, principal root of minus 4 times the, right? If you have this, if we apply this property of radicals, well, then we're going to eliminate the imaginary component, and it's going to be like it was never there when that's not true at all. Minus 1 times minus 1, so you get positive 32. That's incorrect. No, you need to. You don't want to do anything. You don't want to do any kind of math operations at all. Nothing until you've. Okay, well, wait a minute. I can't do anything until I've taken the I out of this. I don't want to do anything here until I've taken the I out of this. Now I can proceed forward. I've got the I's taken out. Now this obeys all the properties of any other math system. I is just a number. All the rules are completely valid. I don't have anything to worry about. Just treat I like it's any other number. It's just the imaginary number. It's just I is pi is just pi. It represents a 3.14, etc. It's the radius of it's the ratio of the diameter of any circle to the circumference. I is just a number that it's a number such that when you square it, you get -1. Or it's the principal square root of -1 is I. That's all it is. That is all I is. Okay? So with that, when it comes to adding, subtracting, and multiplying complex numbers, you don't need to memorize anything. This is extremely straightforward. Dividing it's extremely straightforward as well, but you have to know a trick to be able to do it. And I'll explain why dividing is not quite as straightforward as regular dividing, but it's still very simple. And you'll see what I mean by where the difference comes from. But here, how would you add this normally? Again, if you're treating I like it's like pi or something, well, just add it like you normally would. There's nothing to memorize here. What would you do? Well, you just do this. Now you combine, quote unquote, combine like terms, right? And when you say combine like terms, you're usually thinking about like variable expressions. That's why I kind of said that you think of I like it's a variable, but it's really not a variable at all. I is a number. All right, so 9 plus 3 is 12. 2 minus 3 is -1. Now you're done. And another thing to note is that when you're dealing with any kind of math equation system or whatever, and you're performing operations with imaginary numbers, complex numbers, you could do whatever you want. Again, like I is a number, like any number. You can multiply I terms on both sides, divide I terms on both sides. You can do whatever you want with I. However, when you're coming to the end of the problem, and what we typically do is we clean things up and we put them in a simplified form. You want to, if you have imaginary numbers, you want to present it as a complex number form, the standard form, real part plus imaginary part. Like you don't ever want to leave it like this, minus I plus 12. This is not incorrect. I mean, there's nothing incorrect like from a pure mathematical standpoint about this. It's just you don't present it like that. You want to present it as a complex number, right? You wouldn't just stop here and present this. This is not incorrect. Like from a pure mathematical standpoint, it's just why you don't present this. You show we added 2 complex numbers and we got another complex number. That's the whole idea. So you want to show, okay, well, what complex number was the result from adding the initial complex numbers? Okay, so this minus sign makes this a little more tricky, but we know how to do regular arithmetic. You just distribute that minus sign. So it's going to be plus 4 minus 4i. Okay, these 2 go away, so you're left with minus 2 plus 4 is just 2. You have just a real number, but this is still, like we talked about in the previous videos, this is still technically a complex number, but you just leave it like a real number. All numbers are technically complex numbers. Okay, no problem at all. 2 minus 5i minus 3 minus 4i, then plus 1 plus 9i. Okay, 2 minus 3 is going to be minus 1. Minus 5i minus 4i is minus 9i. Plus 1 plus 9i. Minus 1 plus 1 is 0. Minus 9i plus 9i is 0. This is just 0. Okay, so, we got minus I root 2 minus 2 minus 6 plus 4i root 2 minus 5 plus I root 2. Let's see, is that right? Minus I root 2 minus 2 minus 6 plus 4i root 2 minus 5 plus I root 2. Okay, minus I root 2 plus 4i root 2 is 3i root 2 plus I root 2 is 4i root 2. Okay, minus 2 minus 6 is minus 8. Minus 8 minus 5 is minus 13. Okay, but is this wrong? Did we do something wrong here if we just left it like this? Did we make a math error? No. But this is not presentable. There's 2 reasons why this is not presentable. Number 1, we want to put the real part first. Okay, then number 2, we don't want to write this as 4i root 2. Show the real or the imaginary coefficient. Well, this is actually kind of confusing because we typically put I out front with radicals, so we don't confuse that people don't think that the I is underneath the radical. But so you might do it like this: plus I, like that. So you can clearly see what this is called this is a complex number. This is the real part, minus 13, and the imaginary part is 4 root 2. Okay, that was adding and subtracting complex numbers. How do you multiply complex numbers? Well, I would strongly suggest you don't memorize any formulas. You just multiply it like you normally would multiply anything. And then again, you might be saying, well, why isn't it the same kind of freedom with dividing? You'll see in a second. It really is the same freedom. It's just you have to see a trick that comes into play. So, okay, yeah. So 2 times 3 is 6. 2 times minus 2i is minus 4i. 3i, and then minus 2i squared. There you go. Now, we just remember that if you have I in any expression or equation, whatever, if you have I to a power other than 1, you can always simplify that. You should never leave something with I to a power other than 1. Then it's not wrong. It's just you haven't simplified it. You can always simplify I to a power other than 1. So, okay, minus 4i plus 3i is minus I. I squared is minus 1. So this is plus 2. So you've got 8 minus I. So we multiplied 2 complex numbers and got another complex number. Okay, 2 times minus 1, minus 2. Okay. All right. I squared is minus 1, so minus 2 minus 12. There we go. Okay. 3 minus 2i squared. We just multiply this out. No big deal. 9 minus 6i minus 6i plus 4i squared. Okay, so 9 minus 12i minus 4, 5 minus 12i. Okay, here we're multiplying complex conjugates. So we know that this is going, we can just multiply it out, but this actually simplifies in a lot because of I squared being negative 1. So you've got 3 times 3 is 9, but then minus 3i plus 3i is 0, and then you have minus I squared. I squared is negative 1, so this just comes out to be a real number. When you multiply complex conjugates, you just get a real number. Okay, let's see. These are complex conjugates as well. Because with a complex conjugate, all you're doing is just changing. You have the exact same terms, imaginary and real terms, but you just change the middle sign from plus to minus. So minus 2 times minus 2 is 4. Minus 6i plus 6i is 0. And then minus 9i squared. So 4 plus 10, 14. Okay, complex conjugates again. So root 6 times root 6 is 6. Minus root 6i plus root 6i, and then minus I squared. So 6 plus 1, 7. Okay, so here we're multiplying 2 complex conjugates, but all of a sudden we have this I out here. What's that about? Doesn't matter. I is just a number like any other number. We could do whatever we want. We could put I wherever we want. So, okay. I times multiplying these two, you get 9 plus 12i minus 12i, so then minus 16i squared. Okay, so I times 9 plus 16, so 25i. Okay, so let's see, 3i, 2 minus I. Okay, 3i, we've got 4 minus 2i minus 2i plus 4i squared. Okay, so let's see. 3i, you've got 4 minus 1 is going to be 3. Okay, now distribute this. So 9i minus 12i squared. 9i plus 12. 12 plus 9i. Okay, 4 plus 2i minus 2i minus I squared. 4 plus 3i. Okay. 4 plus 1 is 5. All right. 20 plus 15i. Okay, now dividing two complex numbers. Why isn't this just completely straightforward like we would do any other division? The only reason is because we know that if you have like if you've got 5x plus 2 over 3x minus 7, you can't really do anything with this, right? Because it's if this was a single number, then you could separate it up into two separate like addition of fractions. But just like it sits, you can't really do anything with this. So it's not a big deal. But all we need to do is what we're going to do. The goal is let's turn this into a single number down here. And we know we can do that by multiplying by 1 in the form of the conjugate of the denominator, the complex conjugate. Then we can turn this into a single number. Then we can simplify it and split it up. So, okay, we've got 6 plus 2i, and then 1 minus 2i. Okay, 1 plus 2i times 1 minus 2i is, you've got 1 minus 4i squared. That's 1 plus 4 is 5. Okay, so now we just multiply these two complex numbers like we just did in the previous problem. So 6 minus 12i plus 2i minus 4i squared. Okay, so 6 minus 10i plus 4 over 5. So 10 minus 10i over 5. You got 2 minus 2i. Like that. You see, but we don't want to stop here. We don't want to stop here. We want to split it up to where the idea is we want to take one complex number, divide by another complex number, and then see what the resulting complex number is. That's the idea. Okay, so once again, you just do multiply by the complex conjugate of the denominator. So 2 minus I times 2 minus I, you're going to have 4 minus 2I minus 2I plus I squared. And then in the denominator, you're going to have 4 minus 2I plus 2I minus I squared. So, okay, we've got 4 minus 4I plus I squared over 4 minus I squared, which is 4 plus 1, which is 5. Okay, but now I squared is negative 1, so 4 minus 1, you've got 3 minus 4I over 5. So 3/5 minus 4/5 I. Okay, let's multiply this by 1 in the form of 1 minus I over 1 minus I. So we've got and then in the denominator, you've got 1 minus I plus I. Okay, so in the numerator, you've got 1 minus I minus 3I plus 3I squared over 1 minus I squared, so that's 1 plus 1 is 2. Okay, so you've got 1 minus 4I minus 3 over 2. Okay, so minus 2 minus 4I divided by 2. So that's minus 1 minus 2I. Well, for one, we want to get a single number in the denominator, but also we want to get the I out of the denominator too. Okay, so in this case, it actually would be fine to just do this. You get the same answer anyway, because it's really, it's not about multiplying by the complex conjugate of the denominator. The whole purpose of that is, again, to get the I out and get a single real number in the denominator, which this would accomplish that. So you get minus 5I over I squared minus 5I over minus 1, you get 5I. If you multiply by minus I over minus I, it'd be the same thing. So here you could just, again, multiply by I over I. You get 8I over minus I squared. So 8I over just 1 is 8I. Okay, so like even here, you could, if you think about it, you could just do I over I, and you get the same result. So 2I over 3I squared, well, what does that result in? So minus 2/3 I. So there you go. That's how you add, subtract, multiply, and divide complex numbers.